I've made many videos about many subjects, but one that I've never made is one that tells you about the current and future research program of Fermilab, my scientific home. I mean, there are lots of places one could choose to do research. What is it that makes Fermilab so special? Why did I decide to do research here? And, well, just what is Fermilab anyway? Fermilab is America's flagship particle physics laboratory. Located just west of Chicago, it's one of the world's premier research centers, and it's doing cutting-edge research into some of the most fundamental scientific questions. The facility is located on 6,800 acres, and for more than a quarter century, it operated the Tevatron, the highest energy particle accelerator in existence at that time. Not only is Fermilab physically large, it's also the intellectual home for about 300 resident scientists and postdoctoral researchers, and about 4,000 visiting scientists drawn from prestigious universities from across the world. Fermilab's staff of permanent scientists consists of 200 particle physicists, which is a larger permanent faculty with those credentials than any other facility on Earth. Thus, by that specific measure, the laboratory has the highest concentration of subatomic expertise on the planet. Go big or go home might be Fermilab's intellectual motto. Our focus is on the big, unanswered questions of science. There are many of them. Questions like, how did the universe come into existence? Why are the laws of nature the way they are? Does the universe have to be the way it is, or could it be otherwise? Maybe the biggest and most succinct summarizing question is, why is there something rather than nothing? And, truth be told, we don't know the complete answer to any of those questions. But because of centuries of scientific effort, we've made a lot of progress. We know that the universe began in an enormous explosion called the Big Bang. We've also devised a detailed, if incomplete, understanding of the rules that govern subatomic matter. That theory is called the Standard Model. The Standard Model of particle physics explains the subatomic world of molecules and atoms as being built of 12 even smaller particles called quarks and leptons. Those particles are the smallest known building blocks of the cosmos, and they are governed by 4 forces called the strong and weak nuclear forces, electromagnetism, and gravity. Finally, a ghostly field called the Higgs field gives mass to some of those particles and completes the theory. The Standard Model is well established in universally accepted physics. Researchers used the Fermilab scientific complex to discover 3 of the quarks and leptons you see here. In addition, in 2012, Fermilab researchers played key roles in the discovery of the Higgs field, and they continue to contribute to studying its properties. While those are respectable achievements, researchers are much more interested in the future than the past. What questions are Fermilab scientists tackling now? There are a ton. My personal favorite is to follow in the long-standing Fermilab tradition and look at matter under more and more extreme energies. My colleagues and I collect and analyze data recorded at the Large Hadron Collider, or LHC, located at CERN, which is our sister laboratory in Europe. The LHC is currently the highest energy particle accelerator in the world, and it collides protons together at energies high enough to recreate the conditions common in the universe when it was only a tenth of a trillionth of a second old. There are 4 detectors arrayed around the LHC, and the one that Fermilab scientists are working on is called the Compact Muon Solenoid, or CMS. 3,000 scientists from around the world have joined together to try and uncover nature's mysteries. And together, we've made thousands of measurements, published hundreds of papers, and are looking forward to several decades of future research. And even though the accelerator is located at CERN, Fermilab's research group of scientists, engineers, technicians, and computer professionals is the largest visitor group working on the LHC. But LHC research is by no means all we do. About a decade ago, the decision was made for Fermilab to build a world-leading infrastructure to study the behavior of neutrinos. Neutrinos are subatomic ghosts that interact rarely with matter, and, perhaps even more amazingly, they are particles that can change their identity. The term physicists use for this behavior is neutrino oscillation. In the recent past, in the present, and in the future, the Fermilab neutrino program has been or will be comprised of perhaps a dozen different neutrino experiments with names like Mini-Boon, Micro-Boon, Minos, Nova, Minerva, Icarus, SBND, and well, more. Each of them explores a different facet of the behavior of neutrinos, including the fact that they can change their identity. However, the future will be an enormous experiment called DUNE, short for Deep Underground Neutrino Experiment. In this experiment, Fermilab will shoot a beam of neutrinos from Illinois through the Earth to South Dakota at a huge detector located deep underground in the former Home State gold mine in the town of Lead. This experiment is truly international, attracting over 1,000 researchers from dozens of countries across the globe. DUNE has many goals, but I can call out 3 of them. One isn't to study neutrinos at all, but rather to look for instances where protons decay. Protons seem to be stable, but some theoretical ideas say that maybe they can decay into lighter particles, which is a pretty mind-blowing idea. DUNE will also look for neutrinos emitted from supernovae in the Milky Way and nearby galaxies. Supernovae are rare, with about 1 per galaxy per century, so that takes a lot of patience. But perhaps the most anticipated measurement is one that studies and contrasts the behavior of neutrinos and antineutrinos. Einstein's famous equation, E = mc², is often said to mean that energy can convert into matter and vice versa, and well, that's true. But it's more accurate to say that energy can convert into matter and antimatter and in equal quantities. When one applies that concept to the Big Bang, in which the universe was once smaller and hotter and full of energy, things get a little weird. As the universe expanded and cooled, that energy should have made equal amounts of matter and antimatter, which brings us to a perplexing question. Where is the antimatter? We don't know the answer to that, but it's possible that neutrinos and antimatter neutrinos oscillate at different rates. If the 2 particles exhibit different behavior, perhaps that's a clue that might lead to an explanation. It's hard to say, but Fermilab's NOVA experiment is looking at this, and DUNE will eventually chime in with improved capabilities. The LHC and neutrino programs are both impressive, but they're only part of what Fermilab does. Our scientists are also investigating an earlier measurement that might be the best prospect for discovering new physics. This experiment is called G-2. Almost all subatomic particles act as if they're spinning. Those particles that also have electrical charge combine that with the spin, and the result is that they act like magnets. And if you put a magnet in an external magnetic field, the magnets will precess like a top. That's just what they do. This precession property has been extensively studied for a subatomic particle called the muon, which is basically a chubby electron. Both the calculation and measurement of this property have been conducted to staggering precision, to 12 decimal places, in fact. But here's the exciting thing. The measurement and prediction disagree. Now, when measurements and predictions disagree, that can mean a discovery. But the disagreement has to be large and precise to be sure that it's real, and this particular disagreement isn't quite big enough to be definitive. So, the Fermilab G-2 collaboration is redoing the measurement with much better equipment. If the new measurement agrees with the old one, this will be very exciting indeed. While the G-2 experiment would tell us something about muons in the near future, another experiment called mu-E will study them in a few years. Mu-E will look for an extremely rare decay mode of muons. It's a crazy difficult experiment, and it'll be interesting to see how it unfolds. So let me tell you about another fascinating topic that Fermilab scientists are studying. We're not just studying the subatomic world, we're also super interested in the cosmos as a whole. The statement that the universe is made of matter is hardly an adventurous one, but it's more complicated than you'd think. Astronomers have surveyed the entire universe and determined just how much matter exists in all of the galaxies we see and the gas that surrounds them. Astronomers have also determined how much matter and energy there is in the entire universe, and when they compared what we see and what we know is there, the 2 numbers don't agree. In fact, The matter that makes up galaxies and gas comprise only about 5% the total matter in the universe. So what's with the other 95%? It turns out that 25% of the universe, that's 5 times as much as ordinary matter, is made of a substance called dark matter. Dark matter is thought to be similar to ordinary matter, but it interacts only gravitationally. We're not even 100% sure that it exists, but something is going on because we see its effect and the speed at which galaxies rotate and how light from distant galaxies is distorted on its way to the Earth. The remaining 70% of the universe is thought to be made of a peculiar substance called dark energy, which is an energy field that results in a repulsive form of gravity. Unlike matter and dark matter, which makes the expansion of the universe from the Big Bang slow down, dark energy makes it speed up. Now, neither dark matter nor dark energy are believed at the same level that we believe the Standard Model. But the evidence is awfully compelling, and given that not knowing the nature of 95% of the universe is kind of a big deal, Fermilab physicists are looking, or will look, for these 2 elusive substances with experiments called Super CDMS, COOP, PICO, the Dark Energy Survey, and the Large Synoptic Survey Telescope. Our researchers are as interested in the cosmos as they are in the microrealm. Okay, there's one last initiative that I want to mention that Fermilab scientists are working on, and that's studying the quantum realm, with an eye towards both quantum computing and quantum teleportation. You know that whole is the cat alive or dead thing? Yeah, they're working on that kind of physics, but not with the usual sort of befuddled conversation that often incorporate quantum mechanics. Fermilab researchers, working with academic and industry partners, are actually using the laws of quantum mechanics to develop and build real technical devices that use quantum weirdness to build ultra-fast computers and to be able to transport information from one place to another. The things that I've told you here don't span the full range of scientific and technical projects that Fermilab scientists are working on. We're also inventing and building new accelerator technologies and pushing computing facilities and engineering capabilities to the limit, and tons of other very cool experiments and measurements. Really, it's an honor to work among such creative and smart people. I think I'd be remiss if I didn't mention that Fermilab is more than just a mecca of science. I told you how big it is, but I didn't mention that the whole site is essentially a nature preserve, with the restored prairies, abundant wildlife, and even a small herd of American bison. The laboratory also hosts public science lectures and art and theater performances that are open to the public. We even have a small art gallery with a constantly changing parade of art shows from distinguished artists. I hope I've given you a good sense of what we can do at Fermilab. It's an amazing place, and you can even come and visit us every day of the week. If you'd like to be shown around, we have public tours every Wednesday, and on the first Sunday of every month, we have an event called Ask a Scientist, which has a public lecture and then a couple of hours access to a group of scientists who will try and answer any question that you throw at us. If you're interested in visiting, there's a URL in the video description that tells you the many different ways that you can visit. Y'all come. You get to see some amazing science, and I'm sure that you'll have a great time. So that was fun. I could talk all day about the outstanding science that my colleagues and I conduct every day at Fermilab. It really is an extraordinary place, and, well, I'm lucky to be part of it. If you like this video, please like, subscribe, and share. And I'm serious about inviting you to come to visit and see where new physics is being discovered. And of course you'd like to do that because, well, physics is everything.